The next speaker is Nathan Usevitch from Stanford University. Please share your screen. Nathan will talk about development process of an isoperimetric robot. The stage is yours, Nathan.
Thank you very much for the introduction. My name is Nathan Usevitch. I'm going to be presenting work that I did in conjunction with some co-authors here at Stanford University, as well as Elliot Hawks at University of California at Santa Barbara. And today I'll be talking about the development of this robot shown here, which is, we've been calling it isoperimetric robots. This will dovetail nicely with Mark Yim's talk this morning as well. To kind of give an overview of this robot, it's a robot composed primarily of inflated fabric tubes. It's large scale and it operates fully untethered. So here this robot is grasping a basketball. So 24 centimeter diameter basketball. And you can also see here we're doing kind of like an in-hand manipulation task. My focus today is not going to be so much the details of the robot, but more the development process. So I refer you to this, this Science Robotics paper if you have more specific questions about the robot. So I want to talk though about our inspiration and then why we made the decisions that we made. Our inspiration is actually this exact same video that Mark Yim showed earlier. NASA showed this demonstration of a truss robot that can undergo enormous shape change. And of course, this video is just hypothetical, but we were really inspired by the dramatic shape change this robot can achieve. And we were interested in that capability, both for human-robot interaction, as well as for the ability to locomote over varying terrain. However, it seems like the key challenges of this device is developing actuators with a large extension ratio. And then upon reviewing the literature, one of the key challenges with these systems is that the structure can be incredibly brittle if you build a truss structure like this of electromechanical actuators. So we wanted to develop high extension actuators and a compliant structure. Now, our first thought was that we could take a soft robotics approach to address some of these challenges. With soft actuators, we can achieve high extension ratio and obtain this inherent compliance. And so we worked for several years, developed several different types of actuators and showed some promising results. Here's a tetrahedron and a partial tetrahedron made of different actuators. However, each of these actuators has a fundamental limitation that is quite common to soft robotics, in that the actuation is totally dependent on an off-board air compressor as well as pneumatic control valves. And so we wanted to be able to remove this dependence on these off-board systems, which requires kind of a change in architecture to some extent. Traditionally, we've thought of these truss robots as something that looks like this. Each actuator can extend and contract as we pump air in or vent air out of it, which requires a lot of work from a microcompressor, which either limits the speed of the system or limits its strength. So our new system looked like this. We would take a single continuous inflated tube, we would bend it into a loop, and then we would place robotic rollers at each of the nodes of the system, each of the corners. They would be able to pinch the tube, basically induce the corner, and then be able to drive the corner back and forth along the tube. So with this system, the key here is that the overall perimeter of the robot remains constant, and hence the total amount of air in the robot remains constant, meaning that we don't need an active pressure source. I wanted to highlight kind of the prototype evolution. These are some of the first prototypes we had once we had this key realization to move to this isoperimetric architecture or constant perimeter architecture. We started with PVC and rubber bands, worked up to some laser cut components. These are some of the very first prototypes that we put together of connected nodes in a triangle. We learned a lot of things that don't appear in the model. One is that this low density polyethylene tubing that we were using would actually undergo dramatic plastic deformation. You can see how bowed some of these edges are. So we learned about the importance of making the tube strong. We also, as we would drive these nodes back and forth, we would often get the tube jammed within the roller mechanism. So as we move forward, we added some mechanical guides to ensure proper routing of the tube. We switched to a fabric tube as opposed to a low density polyethylene tube. And you can see here the first octahedron structure that we made. It's barely standing. It stood just long enough to take this picture, but we were able to get this standing structure. Another realization we made is the importance of kind of removing some of in the physical system, there's some non-ideal kinematics. So we had to design a node. We essentially designed a node with a passive mechanism that ensured this robotic roller always sat at the bisection of this angle. something that we didn't see until we actually prototyped the device. And here you can see additional prototypes increasing the size of the tubing, increasing the diameter of the tubing, and as well as moving the stiffer tubing. And in the end, we ended up with a robot composed of these inflated fabric tubes. We designed these roller modules, these robotic roller modules that accounted for this kind of kinematic discrepancy. And then we added these universal joints to connect the nodes together. And so I guess the story here is that from very basic prototypes, we had this very iterative process to move from this basic design to this final design. And in the end, the robot's capable of doing things like this. So here's kind of a locomotion demonstration. And certainly this robot is not high speed and dynamic, but to be at the approximately human scale it's at and to be able to move in real time while untethered is a first step towards some of the inspiration videos I showed earlier. And so in conclusion, I just want to say, recap, we moved from initial inspiration of Truss and soft robots. We developed this new isoperimetric or constant perimeter architecture to overcome some of those different components' respective problems. And the result was that we were able to develop this untethered inflated robot at human scale. And I would love to interact through questions and comments. So if you have any questions, please let me know in the chat. Thank you.
Great. Thanks a lot, Nathan. Very interesting. We move